It's great to be back, and one thing Lou left out is his major role in those Trieste courses, in which he was the co-director after the first one, and really carried a lot of the load. So thanks very much for inviting me. I'm going to come back and talk about these. These are mainly starlings, except for one hawk that you'll see that's driving some of the actions there. And I also want to acknowledge the various funding sources over the years that have helped me. I won't take you through this list, but I appreciate the support. So from microbial systems all the way up to socioeconomic systems, macroscopic patterns emerge from microscopic interactions. The person at the right is my late colleague, John Tyler Bonner, who just died. In fact, the memorial statement for him will be read at the Princeton University faculty meeting on Monday next week. And John was the one who did the fundamental work on the cellular slime molds and showed their importance in addressing a number of issues, largely pattern formation, but also the social dynamics of collective phenomena. John was a wonderful colleague and a real gentleman. So when there are patterns that are going on multiple scales, this inevitably leads to conflicts between levels. So for example, tumor cell growth is an example of the breakdown between the breakdown of the commons. Tumor cells do better within a host, but ultimately they're going to lead or can lead to the demise of the host. And also going back to these starlings, it leads to the need to scale from individuals like this, fantastic patterns that one sees, to ensembles, and then back down again to look at, and I'll come and talk a little bit more about this later, about the consequences for individuals and the trade-offs in terms of their interest. These are public goods problems. What's the public good in the starling? It's information about what to do, and it's also confounding the predator. So if those actions confound the predator, that's great for the group, but why should individuals take risks to be part of that? Public goods problems are widespread, both in biological contexts like the termite mound that you see on the right, but also in socioeconomic and biological context in which individuals are sharing some common resource. What are public goods? Well, Paul Samuelson, the late great economist, said they're goods that everybody enjoys in common in the sense that one individual's consumption of it doesn't affect another individual's ability to enjoy it. They are what's called in the literature non-rivalrous, but they're also understood to be non-excludable, meaning I can't prevent you from enjoying the clean air. And in that sense, they differ from what are called common pool resources problems like fisheries or aquifers. But these are really ends of a continuum, and for the, because if these are different because if I take fish out of the ocean, they're not there for you to enjoy. But for the purposes of this lecture, I will lump them together, and in the literature, there is really a continuum between them. One often thinks about common pool resources as public goods with congestion. One can formulate them in that way. So problems of public goods and common pool resources, and I will probably mainly just call them public goods for the rest of the lecture, are central to our future, to the future. This is in Beijing, showing what the decline in air quality. Anybody who's ever been there or read about it knows about this. And yet, despite the importance of maintaining clean air and things of that sort, we are eroding our public goods. These are two related graphs, one showing projected renewable water resources, the other renewable resources in general, but in the Middle East and Africa, North Africa, but you see the same pattern, that these are declining. So why haven't we solved this problem? I will come back to that a little bit later. So public goods and common pool resources problems are central in ecology. I've already talked about information and tumor growth. Organisms in the ocean will produce siderophores that help chelate iron and other critical things they need. But why is that a public goods problem? Well, if those siderophores are out there, that material, that iron is available to everybody, so why not just sort of steal what's already been produced? The use of water by plants is a public goods problem. Eduardo Zeo was a graduate student of mine working with me and Ignacio Rodriguez at Turbe. Plants take up water, obviously, and they have to balance assimilation and evaporation through stomatal growths. Now, if I'm the only plant in the world, I'm going to conserve that water underneath the meat so it's available for me in the future. But what if I'm not the only plant out there and the water is not staying under me? We looked at this by looking at the mixing rate and found what the optimal in an a game theoretic sense, the evolutionarily stable strategy would be as a function of the mixing rate. What did plants take up? We looked at a game theoretic model. If the mixing rate was low, they took up very little, leaving much for the future. But as the mixing rate increased and it became open access, the game theoretic optimum was to use more. And this comes up over and over again. I'm not going to talk about it, but we've looked at the investment by this is with Ramanand Lakshminarayan and graduate student Sarah Drohan and David Smith, at how much hospitals will invest in protecting against antibiotic resistance bacteria arising. And again, it's very much a function of, in this case, how big the hospital is, how big the city is, whether the patients that I discharge are likely next time to come back to my hospital or some other hospital. Is it a common pool problem or is it my problem? So fisheries and aquifers, and I'll come back to talk about this example a little bit later, presenting analogous challenges to what the plants face. If I'm going to withdraw from a fishery or from an aquifer, if it's mine to preserve, and Colin Clark pointed a lot of this out, then I'm going to be much more prudent in its use. But if it's an open access situation, then all bets are off. Nitrogen fixation is a public good problem. Why? Well, if a plant fixes nitrogen and then drops its leaves on the ground, a neighboring plant can utilize the nitrogen that's been fixed. So why bother investing in what's costly? This is a problem that Lars Sedin and I have been interested in, and we've had a number of students who worked on it. And there are a number of patterns of nitrogen fixation that pose challenges, both in terrestrial and marine species systems. I'm only going to talk about the terrestrial systems now. But the question that is puzzling is, why is there so much nitrogen fixation places where there appears to be abundant nitrogen available? Why isn't there in places where you would expect it to be? So we looked at some mathematical models to try to understand why there isn't nitrogen fixation where nitrogen is limiting, and why in other examples there is nitrogen fixation where there's plentiful nitrogen. So we had a great student, many of you will know him or his parents, Duncan Mengi. And the model we looked at is a model similar to what we also looked at in marine systems. So this is the biomass of the plant. And there are two resources that can be taken up, nitrogen or some other limiting resource. And the standard model is Liebig's model, the minimum, which says that the rate of uptake is some function of the availability of the two resources, and whichever element is limiting growth will determine the growth rate, and so we use the minimum function here. That's not the only function one could use, but it's pretty standard. And what's crucial here is there's an input of nitrogen, there's an input of the other resource, they're taken up, and they're taken up by the plant. And there's also fixation that's going on, and fixation imposes some cost on the species that fixes, and so we focus on these two growth rates. if nitrogen is limiting, then the plant that fixes nitrogen will gain an advantage from this fixation rate. But if the other resource is limiting, all you're doing is paying the price for being able to fix nitrogen, but you're losing as a function of it. So what we did is we put these into competition with each other. That is, we looked at different values of the theta parameter to ask who would win out under various circumstances. So in other words, the model I just showed you is basically assuming certain characteristics, and we look at trait-dependent dynamics on ecological timescales. And then we put them into competition, different strategies, and look at competitive dynamics on longer evolutionary timescales, and ask the question of, in a game theoretic sense, what strategies are most successful at resource acquisition. We did things similar to this with Chris Klausmeyer in marine systems to try to understand the so-called Redfield ratios, why the nitrogen to phosphorus to carbon ratios are fairly constant over broad regions. The basic result is that a co-limited nitrogen fixer evolves. I can explain why it's co-limited if the non-fixer would otherwise be nitrogen limited. And then Duncan and I published another paper which goes back to what I showed you before, how important the spatial heterogeneity can be in these systems, because whether I can steal your nitrogen or not depends on how well mixed the system is. So the same phenomenon over and over again. I'm not going to talk much about antibiotic use, but plants and bacteria produce antibiotics that poison others. There's a cost associated with producing the antibiotic. The question is, under what conditions will antibiotic production evolve? And of course, a very different kind of question involving antibiotic use in human societies involves a public goods and common pool resource question, because we are eroding the effectiveness of our antibiotics. And finally, vaccination's another public goods problem of a slightly different kind. If I get vaccinated, that's protecting you to some extent. So the benefits to the individual to get vaccinated depends on the level of vaccination within the community. Now, interestingly, we have two different problems, one with antibiotic use, in which there's an overuse of antibiotics, and the other with vaccination, in which you've all read about the tendencies towards vaccine hesitancy, and there's an underuse of vaccines. Why is that? Vaccine hesitancy is a problem that's exploding in importance. It's leading to measles outbreaks, et cetera. And so with Ramanan Laxman Rai, and with him in the lead, we got a grant from the McDonald Foundation to run a series of meetings to try to understand, and this is a social norms issue, why is it that antibiotics are overused but vaccines are underused? And I think the simple starting point for this is you take antibiotics when you already know you're sick, usually, and you take vaccines when you already know you're healthy. So I think that's an important ingredient in this problem. But these are both public goods problems. And the last thing I want to mention are in this context, are the extracellular polymers that keep your dentists in business. Bacteria produce extracellular polymers that allow the creation of biofilms. They're signals to others about how prevalent particular species of bacteria are, and they also form a matrix for growth. It's costly to produce these, and yet they're essential for the production of the biofilms, which enhance the fitnesses of individuals. And so bacteria cooperate. They cooperate through what's called quorum sensing, where they send signals, and which are costly. Bonnie Bassler and I had a wonderful student named Kerry Nadell. He's now a professor at Dartmouth. And the idea was to try to understand the production of these extracellular polymers, which leads to, in the technical term, slime, that are produced, and the production of biofilms. Some species produce these extracellular polymers at low cell densities. Pseudomonas aeruginosa produces it at high cell densities, and Vibrio cholera produces the signals at low cell densities, but in both cases, these are signals. So with Carey in the lead and together with Jolly Xavier and Kevin Foster, we looked at a mathematical model that grew biofilms by looking at the interactions between these three types, I should say, of bacteria, those that constituently produce the polymer, those that do it only when there's a signal, either high or low, and those that don't produce it at all. And the model also looked at the diffusion of the nutrient. So what you'll be seeing in here are these colors, and this very much depends on the spatial structure, are these different types of strategies. And we were able to grow, if I say I mean we, if I say we, I mean they did it. We were able to grow these biofilms in silico, and depending on the spatial structure and the movement patterns, one could select for a variety of different strategies. But let me turn now to why Sergei Gavrilets asked me to talk here, which is what are the implications of this for human societies? Public goods problems and the maintenance are problems associated with what's called the tragedy of the commons, an idea introduced about 60 years ago by Garrett Hardin, building on work of William Forster Lloyd 2 centuries ago. William Forster Lloyd pointed out that there are lots of situations where there's sharing of common resources, and how do these get resolved in human societies? If they don't, they lead to what Hardin called the tragedy of the commons. And what Hardin said is the solution to these problems is by mutual coercion, mutually agreed upon. A very nice little phrase, but what he mainly meant was there had to be a role for government to impose rules that maintain this. But it was left to Lynn Ostrom, a late colleague of mine, to show that you didn't need a big role for government. This could arise from the bottom up as long as you had a small society of fishermen, for example, that small societies come up with norms that allow them to cooperate and to sustain the norms. Now this gets harder as those groups get larger, and I'll come back to that at the end. But the small groups formation creates modules that allow for better cooperation. And Lynn suggested in her last years, she died about 5 years ago after winning the Nobel Prize, that international agreements, for example, could be built up this way, say in dealing with climate change, through what she and her husband, Vincent Ostrom, called polycentricity, creating centers of local cooperation that could then be building blocks. And I'll come back to that at the end of the lecture. So let me take you through some of these sorts of agreements. First of all, with work with Avinash Dixit, a great economist, and Dan Rubenstein, a great ecologist. Dan works in East Africa. In East Africa, herdsmen share grazing grounds. And some years are good and some are bad. But cooperative agreements emerge. And so, for example, suppose I'm having a bad year. That is, the climate, the weather conditions are very bad, and there's not enough there to feed my cattle. So I asked my friend Dan Simberloff back there, I said, can I send my cattle over to graze on your land? And you see, he says no, because he's already looked at the model and made a calculation. But I say, but Dan, next year, the situations could be reversed. And so the question is, should he accept my arrangement? Well, I'm going to explain to him why maybe he should. So let's take a simple model. Suppose there are good years and there are bad years. And suppose he and I both are exposed to the same patterns of variation. Now, of course, we could do this with a much more complicated model with degrees of good and bad, but let's just say good and bad years. So in good years, my yield is high, and bad years, my yield is low, and same for him. Now, the question is, suppose that Lou, who is the director of the center, comes in and says, you guys are going to do what's best for everybody. So if he has a good year and I have a bad year, then Lou is going to say a certain number of cattle should be moved from my land to his. but how many? And so we both are making investments in cattle and land. Land is a public good. X are my cattle. And so we set up a model in which we try to find, or Lou tries to find, what would be the social optimum. He's going to choose the transfers to maximize the total welfare. And what I'm going to lay out here, I think, is the way to look at many of these problems in a series of 3 or maybe 4 steps. First of all, we construct a function of this sort. He's got some working group in here to do that. This is the total welfare of the system. So A1 x to the alpha is the payoff in area 1. A2 x to the alpha is the payoff in area 2. A1 and A2 are the yields in that particular year. And so given A1 and A2, we move M cattle that leave this area and go over here. What are these terms down here? Well, these are just the cost of my investment. They don't depend on my strategy, except to the degree they depend on X and Z. They don't depend on the A1 and A2. But this is the cost of investing X1. You can do this with a fixed cutoff too, obviously. So X1 plus Z1 is my total cost, and it doesn't have to be quadratic, but it's got to be something that goes up faster than linear. So this is the total welfare function, and he maximizes this and finds out what M should be. A very straightforward problem. It doesn't have anything to do with my decisions or Dan's. But then the next question is, Lou says, I'm going home. You guys are going to work it out for themselves. Is this self-enforcing? And now Dan has to make a calculation which is based on his discount rate, which may be high. In other words, how much does he care about next year compared to this year? If he cares a lot about next year, then he'll accept my deal. But what if he doesn't? If not, he may come back to me and say, I don't want all your cattle, but you can send me 10. I know I can only send you 10 next year if the situation's reversed, but that's what's called a second best solution. It's not the collective optimum, but it's better than if everybody is just trying to optimize their own payoff. So 3 steps here: social optimum, Nash equilibrium, that's what it's self-enforcing means, and if not, are there second best solutions? Now, there's one other factor, and that's why I said 3 or 4. In these herder societies, kinship and prosociality are important. That is, it may be that my son married Dan's daughter and is over there, and his daughter's living with, so he says, okay, I wouldn't do this otherwise, but for my daughter's benefit, I'll do it. And so I'm going to show you how this can come back into these sorts of calculations later, too. So kinship and prosociality, something that at the working group I'm attending, we've been discussing all day. Prosociality means that I care about somebody else who's not related to me, and I factor that into my utility function. So the central issues more generally, for example, in dealing with climate change, are issues of behavior and culture. Things like intra-generational equity, which was sort of what we've been talking about, and also intergenerational equity, how much do I care about the future? These are problems of public goods and common pool resources, trying to understand how do we get cooperation in the commons. And I'm going to turn to talk a little bit about the role of social norms and institutions like Lou in enforcing this. The most famous example of social norms, I think, has to do with foot binding in China, which obviously wasn't good for the individuals who had their feet bound, but it was something that was enforced by society, because if they didn't bind their feet, they were ostracized in these societies. Foot binding was stable for millennia and then suddenly disappeared over a very short period of time. So understanding how social norms are established, maintained, and then suddenly change is crucial to understanding public attitudes towards, say, climate change. And in fact, we have lots of examples of rapid changes in social norms. Smoking in public places, gender equality, attitudes towards gender equality, racial equality. You saw what happened with flying of the Confederate flag in South Carolina, how quickly the social norm changed. Can we change norms with regard to climate change? And what's the role of leadership and the development of consensus? Okay, so fairness norms, which is Lynn Ostrom's idea can provide a way into these problems. This is work with Alessandro Pavoni and Maya Schluter, both of whom I still collaborate. Maya was a postdoc with me, and Alessandro spent much of his graduate study in my lab. Maya had worked in Uzbekistan on water withdrawal systems from aquifers, but this was really motivated by work on fisheries. And the idea is there's a fishery, and we're all withdrawing from the fishery, and we can, following the example I just showed you, we could all agree to withdraw at the social optimum, or we could all just do whatever we want, or some of us could agree on the social optimum and some of us be selfish. So we looked at a model initially where we have cooperators and defectors. The cooperators are those who withdraw at the social optimum. And actually this term should be a small e because the payoff to that individual is the amount of effort, which is what E stands for, that individual is exercising, and R is the level of the resource which has its own dynamics governed by what people are withdrawing. The payoff to the defector is going to be a higher function depending on his effort and the resource level. But then there's a cost because the cooperators get together and they say, we will punish the defectors. We won't do business with them, okay? And so I won't, this is the reduction in the fitness of the defectors. It's based on the difference between the payoffs. But the most important part is this so-called ostracism function, which depends on the number of cooperators. So the dynamics we have here is we have a certain number of cooperators, we have a certain number of defectors, and the cooperators are imposing a cost on the defectors. The dynamics of the change in the frequency of cooperators is given by this equation here, which comes straight out of, this replicator equation comes straight out of game theory. And there's a separate equation, which I didn't show you, for the dynamics of the resource. And this is what the output of that model looks like. On the bottom axis is the frequency of cooperators. On this axis is how selfish the selfish individuals are. In other words, if it's, this is the amount they withdraw compared to what the cooperators withdraw. If it were 1, then they would be basically cooperators. If it's 3, they're really selfish. And what we find in general is a general pattern, which is there are 2 possible equilibria. This is what's called a coordination game. That is, you may end up heading down to a highly exploitative situation where there are no cooperators. But if you can get the number of cooperators above a certain threshold, then the system goes to a cooperative equilibrium. Not a cooperative equilibrium that's the social optimum, because not everybody's cooperating, but just like in the other example, it's a second best solution. Essentially, you're better off than you would be if it's everybody for themselves. Now, we continue work on this with Andrew Tillman, part of his thesis work, and James Watson, who was a postdoc with me. And the main difference that Andrew imposed was he said, okay, let's allow not just for the for individuals to withdraw at the social optimum and individuals to withdraw at what the individual optimum would, but let's look at all the levels in between and ask, is there a real second best solution in which individuals withdraw more than would be the social optimum, but less than everybody for themselves, and enough to establish a Nash equilibrium? What's the optimal level to withdraw in order to get agreement? So there are a lot of problems that have basically the same sort of structure. So far, I hope I've showed you that collective action can be effective if it includes enforcement, like in this last example of ostracism. That prosociality is an important contributor to the maintenance of public goods and common pool resources. And so now I want to ask, how are collective decisions made, including the fact that if prosociality is important, that I want to be in a society where there is prosociality, and I want my children to be in such a society. So how can I ensure that? I will come back to that at the end. So I want to talk a little bit about work that comes from, that started someplace else, I mean, intellectually someplace else, with my collaborator and former postdoc, Ian Cousin, going back to the bird flocks and then reaching over to human societies, understanding the dynamics of these groups. First of all, their collective dynamics, and secondly, the role of leadership. So this was a paper we published back in 2005. And what we did is we started out with a model of individual fish. Every fish is choosing to change its directions at each point in time based on whatever other outside information it has, including its opinions, and also based on what its neighbors are doing. And that outside information may be good or bad information. That's not relevant to what I'm talking about. So this is an agent-based model. At each stage, each individual updates the direction it's moving based on its information vector, G sub I, and a social vector, which is some combination of the positions and velocities of the other individuals in my neighborhood. And we've done this with, together with Naomi Leonard and a variety of students for all sorts of different topologies. And the important factor here is this weighting omega. If omega is 0, that means individuals are doing nothing but following other individuals. If omega is nearly infinite, then individuals are like politicians and pay attention to nobody else. And so I will show you a couple simulations, a few simulations, in which different individuals have different degrees of leadership and following. So in the first one, there's only one individual who knows where it ought to go. That's the white dot you'll see. And she wants to move up here, and the other 99 individuals are just followers. But because the leader has some component of social information, that this glob doesn't go anywhere, at least not on any reasonable time scale. But if I change that to 5 leaders, they find their way to the front, like in the slime mold, and the slug moves haltingly, but up towards the goal. And if there are 10 individuals there, the group moves very quickly up towards the goal. So this shows us that it doesn't take very many. Now think, this is about fish orienting in space, but think about it in terms of attitudes and opinions in our societies. So it shows that it doesn't take very many individuals to lead a group. These are groups of different sizes. This is the proportion of informed individuals. It's probably more informative to look at it in terms of the actual number of informed individuals. And you see, no matter how big the group size, by the time you get up to 5 or 10 individuals, the group moves rather effectively towards the goal. This is the speed or accuracy with which it moves. Now, what if not every, it was where all the leaders were going the same place? What if they're not going the same place? What if they disagree? Well, a variety of things can happen. I'll just show you one. Here's 5 individuals want to go north, 5 want to go south. The group can't decide, and it splits apart. In other circumstances, they may go up and go back and forth between the goals. So when does this happen? And what do you need to develop consensus? Well, it turns out, and I will come back to this point later, but what's very important here are the independents. What's very important are those who are undecided and can provide the glue to hold together the population and to create the sudden shifts. So collective decision-making is crucial to solving public goods problems. And one of the questions that comes up is, okay, what's the optimal strategy? How many neighbors should one depend upon this in a leadership situation? This is a slide produced by my former student, Danny Grunbaum, although when I told him about it, he didn't remember it. Danny was working on krill and how they oriented in space. That's a whole separate story, but let's suppose that krill are searching for food, and this is some resource spectrum. Well, if there's only one krill there, and it's here on the resource spectrum, the simplest thing to do is to follow some gradient and end up here, which is too bad because she'd really rather end up here, right? So some degree of information sharing would obviously help the situation. So suppose everybody just shared information and decided to follow everybody else. Well, then you get everybody in one nice little cluster, but wouldn't have anything to do with where the resource was, right? So the best thing to do from the collective point of view is to have some leaders and some followers. Maybe permanently, or maybe individuals take turn, whatever. But that may not be a game theoretic solution. Suppose that the group is doing that, I just come along and free ride on it. It's costly to gather information. So the question that arises is, how does selection at the individual level shape the trade-off between tracking resources and tracking other individuals? Behavioral ecologists will be familiar with this, with the producers and scroungers and things of that sort. So we've done a number of things in this category. I will tell you, the questions are: how many leaders, how many followers, what would be the group optimum? Same thing that came up in the other examples. Is there a Nash equilibrium, and otherwise are there second best solutions? And what are the lessons we can draw for cooperation in public goods situations? So I had a student named Eleanor Brush, finished up a few years ago, who set out to look at this problem. Now, I've been working with Naomi Leonard, who's a control theorist, for a number of years. And Naomi has been very interested in collective behavior in animal populations because she puts out sensors in the environment which communicate with each other, and she's interested in distributed control. But there's a big difference between what she does, which is top-down, and what animal groups which will do, which are bottom-up. Various studies have shown that what those birds really do, at least under situations when threatened by a predator, is to pay attention to approximately their 7 nearest neighbors. It's not a geometric thing, it's more of what's called a topological thing, because it's the number of neighbors and not how far away, given that they're not too far. And so Naomi took that work, and in her group, she showed that actually made the groups the most robust and most able to navigate. But what Eleanor did was to say, okay, but I'm an individual fish or bird in that case. Why should I care? And so in this paper, we looked at, remember what we means, we looked at the game theoretic optimal strategies, and it depends on whether they're trying to escape from predation or whether they're collectively looking for food, et cetera. Going back to the work with Ian, we then set out to ask the question, okay, what can we learn? First of all, how can we modify the original model? And I'll tell you about that. And secondly, what can we learn about human societies from this? So in this paper, which we unfortunately called uninformed individuals instead of unopinionated, that they can promote democratic consensus. And there were 4 steps in this. First of all, Ian does experiments where he trains fish to targets and then looks at how collective behavior emerges. Secondly, were the models I've already told you about. And third are some models of decision-making in human societies. And I forget what the 4th was I was going to tell you about, but it's okay. As I mentioned to you before, we found out that unopinionated individuals are really important to deriving consensus. So this is what we did. We said, okay, suppose now I've got a subset of individuals who want to go here to A and a subset who want to go to B. The subset that want to go to B is smaller, but they're really more stubborn. So they really hold to their opinions longer. So this is the strength of the minority opinion. And the question is, what's the probability of reaching the majority target? And not surprisingly, that depends upon how stubborn the minority is. Think about the political parallels here. So if they're not very stubborn compared to the majority, then you're going to end up at the majority almost certainly. And this is exactly what you would expect. These are different strengths, different underlying strengths. The the more stubborn the minority is, the more likely they are to win out. But then we looked at another feature, which is we threw in what you saw there were no uninformed individuals, no unopinionated individuals. Suppose you increase the number of unopinionated individuals, then things get interesting. As the number of opinionated individuals increases, that increases the probability that the majority viewpoint will win out. That is, the stubbornness of the minority becomes less important up to a certain point. But eventually, you're just going to swamp this with uninformed individuals. And if you swamp it with unopinionated, I'm trying to clean up my language here, unopinionated individuals, you end up with almost a random thing where the probability where nobody's opinion makes much difference. So you would expect that, an interesting outcome anyway. So there's an optimal number of unopinionated individuals. We then looked at some models of human decision-making, borrowing from this model of Wheppe and also model of Peyton Young. That was the fourth one I was going to tell you about. But let me tell you just about the structure of these models. We have a network with a large number of nodes, essentially a random graph. The graph degree means the number of connections an average individual has to other individuals. So individuals have opinions, and they go around, they ask everybody else, what's your opinion? And a focal individual will change its opinion with a probability that depends on the number of individuals with other opinions that it's connected to. And there are a lot of models of this sort that we've looked at and continue to look at. There's also a random probability of just spontaneously changing your opinion, having nothing to do with anybody else. And then on a longer time scale, individuals can make or break their links. Longtime members of the Republican Party might decide this isn't my home anymore, I'm going to switch and become a Democrat, or vice versa. And so there are two time scales. One is you make opinions based on the group that you belong to, and two, you choose to join or leave groups. And similar phenomena to what you just saw exist. Individuals have a preferred state, and that preferred state can affect these probabilities. Now, in the last part, I wanted just to ask, can these models of cooperation be extended to the global level? Lynn Ostrom, in one of her last papers, as I mentioned earlier, talked about a polycentric approach for coping with climate change. And Andrew and Avinash and Tillman, Avinash Dixit and I have looked at models of that sort, and I'll tell you a little bit about the structure of those models. So the population is now organized into groups. In related work, we're interested in how these groups get formed. And individuals make decisions based on what's going on within their group and what's going on in other groups. And the simple structure of the model is the following. The fitness or the utility of an individual I in group G is some function of its investment in itself and in the public good in group G. There's this familiar cost function now, but there's an additional term which is the utility minus the cost of the other individuals in your group multiplied times how much you care about them. That's your degree of prosociality. Now, there are other variants on this. You can care about individuals in another group, et cetera, but I just want to make it simple. So Z of G is the public pool in group G, and that may be based not only on the investments everybody in your group makes, but makes some leakage of the benefit from other groups. For example, if you're dealing with clean air or something of that sort. Gamma is the prosociality within the group, and X and Z are, as already earlier, the private and public efforts. Avinash had looked at a single group before, found a game theoretic solution for X and Z, and he found that if prosociality is low, below some threshold, there's no contribution to the public good. But if the prosociality gets above a certain level, then there will be positive contributions to the public good, and you can get cooperative solutions. In the limit, as gamma tends to 1, that is, you care about others as much as you, the solution will move to the collective optimum. But what Andrew and Avinash and I have done is now to look at the structured population where you optimize the utility with respect to X and Z and show that the public contribution at the global level can emerge, just like Lynn Ostrom proposed, because of local prosociality. It can produce global cooperation. But where does this prosociality come from? And Avinash and I have a paper showing that parents can instill this. That's in this paper here. So how does the model in this paper work? Well, I care about my children, and I think they'd be better off to live in a pro-social world. So the model we looked at here says, are parents willing to pay a tax which will introduce education into the school system, convincing the children of the others of my students of my children's generation that prosociality is a good thing? And my willingness to do that is because I want my children's utility as part of my utility. So this is a somewhat complicated game theoretic model, but what it shows is that prosociality can arise, can be selected for because of this mechanism. And these are the examples I gave you before of social norms. Social norms can be a problem, but they can also be part of the solution. So I think in dealing with climate change, the real challenge is to change social norms and people's attitudes. Ernst Fair is well known for the work he's done on social norms. He takes a group like this, and I play this game in my class, it always works. Everybody's given a certain amount of resource, you're asked to spend it on yourself, contribute it to a public good, or use it to punish individuals, presumably, who don't contribute to that public good. The game's played repeatedly. Initially, people are somewhat selfish, but some will punish, and that drives cooperation up. And so, even though it's costly to individuals to punish, they will punish others who deviate from social norms, even at cost to themselves. Punishment itself is a norm that will evolve from repeated interactions. These norms are important to understand much pro-social behavior. And eventually, if these norms work, they become formalized into laws that thou shalt not kill, or else you'll go to jail, and to rules and laws, etc. Social norms are important. I stuck this slide in at the last minute. It comes from Resources for the Future. I think about 10 years ago. It was a multi-country study, the US, China, and Sweden, on attitudes towards climate change. Is climate change a problem? Are we responsible? Can we do something about it? Are you willing to do something about it? And the answers were almost always in the same direction. In the group I was talking to today, the feeling was, well, 70% of the people in the US think climate change is a problem. That sounds good. Not if you compare it to Sweden and China, where it was more like 95%. So what accounts for this? Why? What is it about our society? You can make a case as to China being very top-down. Sweden has a different explanation. The US really does not look good compared to 73% compared to 96 and 94. Norms are dynamic. Paul Ehrlich and I wrote this paper 15 years ago, actually, on how norms change. And here's some evidence on that. These are attitudes in the US towards, this is from Yale and George Mason University, towards climate change. In 2008, 51% of the people were either alarmed or concerned about climate change. In 2010, it had dropped to 39%. It's back up to 45% 3 years ago, and I'll show you in the next slide. It's back up to about where it was. Why? What happened in 2008? There was a financial crash. During the financial crash, people said, I'll worry about climate change later. I got more immediate problems. If we stop economic growth, I'm going to go bust. And so external events can suddenly shift attitudes and norms. And here's a more recent thing. This goes up to 2018, showing an increasing number of people who are concerned and convinced that global warming is happening. But the increased concern is mainly tied to political parties. So this idea that individuals are organized into groups, those groups have attitudes, et cetera, is driving this. You can see among Democrats, it's gone from 64% to 94%, liberal Democrats that is, in just 6 years. There's been some increase among Republicans, but nowhere near as dramatic. So does the group determine your attitudes, or do you choose your group based on your attitudes? Well, the answer is both, of course. This is just from a few months ago. And I thank Steve Pacala for making me aware of this study. So we've been doing some work on this. This is together with Elke Weber, a wonderful social psychologist at Princeton, and my postdoc, Vitor Vasconcelos. And this builds on some earlier models that Rick Durrett and I developed. And in this model, we have a population of individuals. Individuals have attitudes and opinions and group belonging, which are given by a bit string that characterizes that individual. Groups have attitudes and opinions as well. Crucial in this, which is different than what Durrett and I had done, is that individuals belong to multiple groups. That turns out to be really crucial in getting cooperation. So you all come from particular family situations, and then you come and you're at the University of Tennessee, and you belong to other groups probably, and you have to take actions which relate to whatever influences you're getting from all of those groups. And so in this model, just like in the model I showed you before, attitudes and opinions change in relationship to the norms of the group you belong to. And then on a longer time scale, you might choose to move from one group to another, and group dynamics might change, their attitudes and opinions might change. So we have a big project on decarbonization. This part is on India. The technology is there for decarbonization, but how do you get people and leaders to accept it? So that's what we're trying to understand. In related work with Vitor, Phil Hannum, who was a graduate student at Princeton, and George Pacheco, who was Vitor's major professor, we're looking at Lynn Ostrom's ideas in terms extending that model I just showed you up to where the players are nations. And the basic model here is that individual nations belong to groups. That could be like NATO, the UN, the WHO, et cetera, or just some separate agreements on trade, which we used to have. And you pay a price to belong in the group, and if you're not in the group, you're an outsider. But you can belong to multiple groups. You see, that's crucial here. And then once you're inside that group, you can pay an additional price which says, okay, I'm going to mitigate. But your decision to mitigate is based on your membership in all of the associations you have. There's an additional cost, there's an additional benefit to belonging for it. And also in separate work, we've been looking at the dynamics of political polarization. In addition to whether to mitigate or not, you actually make decisions as to whether you're to join a group or not based on the preserved's payoffs. And I'm not going to take you through the details of this model, but this is the output from the model. One of the interesting things, of course, is that you can get cooperation in international agreements. But to me, the most interesting thing is this is basically the number of overlapping groups that an average nation can belong to. And increasing the overlap of group belonging increases the non-excludable public good that everybody benefits from. So there's some hope there. So let me conclude from that model is that sustained cooperation is possible, even though there will be some nations still free riding. Just like with the fisheries example I showed you, most international agreements are structured so they don't go into effect unless the number of countries that sign on is above some threshold. It's basically the same thing. Cooperation in small club configurations yields larger non-excludable public benefits. That's what you see here. So just to conclude the lecture, public goods and common pool resources problems represent fundamental challenges, not only in biology, but in socioeconomic systems as well. We need to address them to deal with climate change and other global issues. Collective action can emerge from local interactions. The problem is played out on multiple scales, and collective decisions from the bottom up can impose mutual coercion, mutually agreed upon. And finally, linking these is key to understanding the management of the commons. So thank you very much.
We have a few minutes for questions. Please use the microphone if you have a question. We want to start off.
Professor Hastings.
Professor Levin. So in terms of say, even in the U.S. or changing opinions, that interactions clearly are important. If you only talk to members of your own group, you're not going to change your opinion. And how, I mean, one can begin to create models that would have this kind of structure and look at that. And
Yeah, so that's why I threw up, it was a throwaway line there, but it's something that's occupying a lot of attention, the relationship between these questions and the dynamics of political polarization. I gave a similar lecture, Lou was there, on
Yeah, it was 50%.
I gave a lecture on Friday at Rutgers, where somebody asked me about how to explain what's going on in the White House now. And I said, to understand what's going on there, you have to understand that it's not the product of one person. It's a product of increasing polarization in our society. And the increasing polarization in our society means that there are factors I didn't talk about, like punishment for deviating from the norms of your group. Well, I mean, I talked a little bit about that with it, but not in terms of opinion dynamics, and how difficult it is to go out and interact with other groups. And that's leading to an increasing polarization in our societies and in our Congress, which co-evolves with opinion formation. So I think that's an important ingredient of what's going on here. And I don't know if it's a mystery, and I think it is to some extent a property of the particular system of governments the U.S. has. It's interesting to compare other countries in terms of how polarized they are, but we're seeing an increasing tendency globally, I think.
Somebody else?
I come from a very different background than nuclear physics. So it's very impressive, all the qualitative models you're having. How far away are you? Right underneath.
You're too close, actually.
Just yell it. The question is, how close are you? How close are you to actually making predictions? You know, like weather forecasting, 50 years ago it was nearly impossible to go more than 1 or 2 days, and now they can go far. All these very, very interesting qualitative models let us understand society much better. But how far are you from having a big complex system where some of these coefficients are being determined, so you can determine what happens at the next election, or what happens with our attitude to climate change over the next 1 or 2 years? Or is that all possible now?
Well, so there are various purposes that models serve. One of them is prediction about the future. I think the most useful part of these models is going to be understanding how it is that one affects, understanding how it is that changes in social norms have occurred, understanding how one can influence that. Now, there are those who would think that it's not a scientist's place to try to influence public opinion, but I'm too old to worry about that. So the question is, so the work that we're doing on decarbonization in India doesn't set out to try to predict, is this going to happen, but it rather, we're trying to couple in surveys of people. How is it that you make your decision? I mean, this is what the surveys are. How do you make your decisions? Whom do you listen to? Where are the critical nodes in the network? You know, those sorts of models were extremely influential in recent elections. Duncan Watts and others have looked at how information gets spread, where's the best place to insert it. So I think of these more with a different purpose. They're predictive models. I mean, it's the same problem that we have in a lot of evolutionary and ecological problems. Is as Francois Jacot pointed out, prediction about, especially about the future, is really hard. Prediction is going to be hard, but trying to understand how we got here is perhaps an easier problem, and maybe we can use that information to develop effective strategies. Also, related to that is the question of how do you structure international agreements to make them robust against cheating. That's not a prediction problem, I think, but it still seems to be an important thing to do.
One more.
Thank you, Sam.
Hi, Paul. How are you?
Very well. How are you, sir? So public good discussion has been very active as an area of research over the last few decades, and a lot of what has been sort of developed talks about contemporaneous interaction neighborhoods and groups. So optimal group size, optimal composition. You were talking to us about that. I'd be interested to hear you map some of that into the intertemporal counterpart. So my discount rate encodes an interaction neighborhood. It encodes a certain number of people that I'm willing to bear costs for today to benefit in the future. So I wondered if you could map some of these developments into that intertemporal domain.
Well, I mean, I think the answer, I'm not 100% sure this is the question you're asking, but I think the answer in terms of strategy is to create local benefits, to convince groups locally that they ought to cooperate together. There's some incentive for solving the problem locally. I think that was Lynn Ostrom's point of view. Even if those are a few nations that get together and get agreement, don't try and get agreement among 200 nations all at once on climate change. It's not going to work. Even if Paris had held, or Kyoto, in order to get it to work, you had to water down things. So make the changes local and effective. And the same thing if you're going down to the level of individuals and societies. I think you have to localize the benefits to them so that they see the payoffs.